Today we're going to be going over block diagram basics, just what you need to know for the first midterm, give or take. We're going to start off by looking at the transfer function formula, the h of s, and you can actually turn this into a form that we're going to be using for the block diagrams, which is b times c, those are both scalars, over s plus a. We remember from our last class, that when you only have one pole here, you only have one pole here, is what this is saying. There's only one root in the denominator, so there's only one pole. And because there's only one pole, the block diagram is only going to have one integrator in it. And then another good thing to know is that the b and c here are interchangeable. If you have b times c equals 10, b can be 2, it can be 5, it could be 1, it could be 10. As long as b and c multiply to 10, you are good. The next thing we're going to take a look at is the standard diagram. So these have a bunch of components to them that Dr. Summer should have gone over in class, but you have the integrator, you have the summer, and then you also have these scaling factors. So the general block diagram situation that we're going to have, and this is good to put on your cheat sheet because you can just basically copy down block diagrams from it, has an integrator over here, and then it's going to have a negative a here, b and c, and remember those are interchangeable, and then a d here. So we can compare this back to our original formula, and we can see that the d goes here, negative a goes down here, and then b and c go over here. The 1 over s is our integrator in this case. So we know that whatever comes out, we can label as x, and whatever goes in, we can label as x dot, right? Because it's getting integrated to x. The other things we can label down here, we have a u of t or u of s going in, and we have a y of t or y of s, depending on what domain you do it in. Coming out, I'm putting this in the Laplace domain because we have an integrator that's represented by 1 over s. So when you do a Laplace transfer, you multiply by s if you're taking the derivative. Here we're dividing by s to take the integral. Snazzy. We know that whenever we read block diagrams, on some of the past midterms my year, fortunately not my actual midterm, but there were these really funky looking block diagrams and they were kind of intimidating, but they all kind of boil down to this basic standard version. And remember that you can go back here. So if we take a look at the y, we know that the y is actually the sum of two things. We have the sum of d times u of s and of c times x. Now keep in mind when you're writing your transfer function, you're going to want to not include the u of s because the entire thing gets multiplied by u of s as a consequence of the y over s equals h of s formula. I digress. But this is just for the sake of reading the standard diagrams. You can also always note here, you can solve for your x dot. We always know that our x dot is x, follow the arrow, times negative a, and then there's a summation plus b times u in this case. And this will come into play more in the later sections as well. We also have a simplified version of the block diagram. My TA gave this just to also have on our exams, where there's only a b here, the integrator here, and then a negative a. I want you to notice that there's just a line here. There's no c in this case. And that's because the c here is a 1. And if it's a 1, you just have a line instead of a line with a box in it. There are also a few ways you can manipulate these block diagrams. So if you're adding two h of s's, two transfer functions, h1 of s plus h2 of s, you're going to put their block diagrams in parallel and then add them with a little summer. So don't mind the funky drawing, it's late at night and I want to go to bed. We have our h1 here and our h2 here. U of whatever variable we're doing this in this case, let's call it t. t, because why not? And y of t there. So when you do this, you're going to get your h1, and then you're going to add it to the result of your h2. And that's going to give you your y. If you're doing it in series, the block diagrams or the transfer functions are getting multiplied. So you end up with your h1 here, and that goes directly into your h2, and that goes to your y. So u, y, and this should technically just be a line. You're not adding anything, you're just going straight into the next one. You can also derive the ODE from h of s, and this is because h of s, as we know, equals y of s over u of s. So your ODE is going to be in the form of y of s something 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 equals u of s something something something. And this will make more sense with an example. If we say our h of s is s plus 3 over s squared plus 4s plus 4, for the record, this factors to s plus 2 squared, so nothing cancels, there's no pole zero cancellation. We can set this equal to, as we know, y of s over u of s. And then to get our ODE from this, we can cross multiply. So we have s plus 3 u of s equals y of s times s squared plus 4s plus 4. And that turns into s u of s plus 3 u of s equals s squared y of s plus 4s y of s plus 4y of s. Now this should look familiar to you. If you want to pause the video and try to figure this out from here, feel free to. But otherwise, this looks a lot like a Laplace transform. Then we can take the inverse Laplace transform to get back to our y of t. Remember that when you multiply something by an s, you're essentially taking the derivative. So this actually turns into u dot of t. So this 3u of t equals, in this case, you have a y double dot of t plus 4y dot of t plus 4y of t. And that is your ODE representation of the transfer function. That covers everything for this video. It was quick. Good luck on your midterms, and thank you for watching.